All I want to do today is I want to go through some practice problems of what we've been doing. You guys doing them at your seats, and then we'll discuss procedures, ask questions, that sort of thing. Some of these get a little bit more difficult, and hopefully we get to a point where we can start talking about some of these stored problems that we have built down here as well. But the first one I want you to do, just to get in the mode of the process, go ahead and solve question number 1 there. Solving for x, and there's multiple ways you can do that, but use the knowledge that we've attained to solve for x there. I'll give you about 2 or 3 minutes to do that. All right, so if we go, so the nice thing about this is because it gives 2 angles, we could do this 2 ways. We could do this even if they just gave us 1 angle, but we can use the other angle to check our answers. Does that make sense? Okay, so let's say that we've got the 32. So if you use the 32, you know you're going to have to use this side here, right? So what side is that? Opposite. And you're going to have to use that known value there, right? So that is adjacent, correct? So which trig ratio uses opposite and adjacent? Tangent. Okay, remember Sohcahtoa. So tangent is opposite and adjacent. So we're going to go tangent 32. So then what are you going to do next? Multiply both sides by 22. And that'll give you 22 tangent of 32 is equal to x. So we type that directly into our calculator, making sure that we're in what mode? Degrees. So we're going to go 22 tangent 32. And that will spit back 13.747. Okay. So that's our x value, right? Okay, now let's say that you were a person that wasn't confident in that. Let's look at the 58. Okay, what is this side? What is 22 in regards to 58? 22 is now opposite. And this would be, x would be adjacent. So if I went tangent of 58, now I'm looking at opposite, so 22 over adjacent, which is x, right? Has anybody, as we've done these, has anybody recognized a pattern that happens when your denominator is the variable here? Say that again. Yeah, I could, but I'm still going to have to divide, or I'm still going to have to, so if I divided, because this I would agree that we could write this as, I'm going to write it over here, tangent 58 is equal to 22 times 1 over x. Does that make sense? That's still 22 over x, right? So if I divide it by 22, I can do that, but now it gives me 1 over x. Does that kind of make sense to everybody? What can I do? What can I do with that, though? Well, this might be an approach. What can I do with that to make it just x? I can multiply it by x to both sides, but if I find because this is a proportion, right? If I find that reciprocal, what's that one's reciprocal? X over 1, isn't it? But if I take the reciprocal of that side, what do I need to do that side? Take the reciprocal. So if I go 22 divided by tangent of 58, that will give me x. Okay? But just because this variable is in the bottom, it doesn't matter what's in the bottom, whether it's a number like it was up here or it is the variable, I still have to multiply both sides by that thing. And they cancel it because I got to get rid of the fraction. So I do that. So I get now x times tangent of 58 is equal to 22. And now how do I get x by itself? Here's where I would divide by the tangent of 58 now. Does that make sense? Now divide by tangent 58. Tangent 58. Those will cancel, giving me the same thing that we found right there. Okay? But look at what happened. Look what, if we go back to the original, this is what I was trying to get at. The original said x, not x, tangent 58 is equal to 22 over x. What changed spots? Yeah. The algebra will always be the same. If that denominator is your variable, the algebra will always be the same. So if you want to circumvent a little bit of it, you can basically just take this thing right here and that thing right there and interchange their positions, and you'll solve for x. Okay? That's the shortcut, and I think shortcuts sometimes create confusion. They limit your understanding of your algebra. So before you start using that, understand why you can use it. Okay? Whenever we have a fraction, whether that fraction has a variable in the bottom or not, you always try to get rid of that fraction as soon as possible by multiplying by that LCD, the least common denominator. In that case, we're going to multiply everything by x, and that gets rid of the fractions. And once we do that, then it will generate an equation that we're more comfortable solving with no fractions. Is it okay with everybody? So then when we just check this on Desmos, so we had, what was the first one? 22 tangent of 32. And the last one was 22 divided by tangent of 58. Oh, we must be wrong because those are different numbers, aren't they? But if we did everything right, those shouldn't be different, should they? They should be the same. So what does that tell me about my calculator? My calculator's in the wrong mode. Because when I open up Desmos or any calculator, even your calculator, like sometimes these calculators will reset themselves, like a TIE 384 will reset itself when I turn it off. You want to check that mode every single time. Okay? So there we see if we put it in degrees, they are the same. Is it okay with everybody? Okay. Let's see here. Do question 8. What trig ratio do you have to use on question 8? Okay. Okay, so you can use, so this is just one thing that, just a side note before we move on. Even though it's abbreviated that way, and it's abbreviated that way, and it's abbreviated that way, okay? Think about how when you're reading something in a textbook or just literature in general, let's say I started listing things. Okay? When you list things, maybe we're listing characteristics of somebody. We list 2 or 3 things, and then we write ETC. What does that stand for? Etc., right? So when you read these things, you say blah, 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 etc., right? That's how you read it. You don't say blah, 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 right? Because that's how you would enunciate ETC, right? So when we look at sine, cosine, and tangent, they're the abbreviations for sine, cosine, and tangent, okay? Just fight a lot of times, and this is just practice. A lot of times in like even higher level math, you'll hear people say like tan of an angle or whatever. They should say tangent, but that's the one that's usually most accepted to say the abbreviation, but sin and cos are not. Okay, so when you're going through these and you're reading them, we want to use the entire word, sine, cosine, or tangent. Just the reason I talk about that, I was in school in college. I had a professor kind of berate a student because he kept calling them sin, cos, and tan. And like even when I get to secant, cosecant, and cotangent, like cosecant, I mean there's no vowel there, right? So that's kind of, I mean, how do you say that? So we want to pronounce the whole word. But are we restricted here? Why not? So when you're given every side, I'm given the opposite. Here I'm given the adjacent, and here's the hypotenuse. You have freedom to choose any ratio that you want, correct? Okay. I always go to the sine function for whatever reason. I don't know why, but if I go sine of y is equal to opposite over hypotenuse, so 8 over 17. You guys remember yesterday, how do you get, if that y value is stuck in the parentheses, we call it the argument. Okay, if it's stuck there, you remember how you get it out? Take the inverse. Okay, so we go sine inverse of this side and sine inverse of that side. Does anybody remember another notation for sine inverse other than that -1 symbol? Good. So we can use either one of those, whichever you prefer. It doesn't matter. But that would be one way of doing it. Okay. If I did cosine, anybody do cosine? If I would have gone cosine of y, what's cosine of y? What's the ratio there going to be? 15 over 17. And if I inverse both sides there, it would be cosine inverse here, cosine inverse there. There's a direct cancellation there. It leaves me y equals cosine inverse of 15/17. And the last one we could do would be tangent. So tangent would be tangent of y is equal to opposite over adjacent, so 8/15. We'll inverse both sides. And those will cancel, leave me y equals tangent inverse of 8/15. Okay? Now, obviously you don't have to do all those. You were only looking for y, and we want to get it as fast as we can. But my thought is, if I'm uncertain, at least being able to show you multiple ways of getting the same value can maybe confirm an answer for me. Okay? So I'm going to type in arc sine of 8/17. And that's 28 degrees. Okay, I'm going to type in arc tangent of 8/15. It gives me that number right there, 28.07. And I'm going to type in arc cosine then of what should be 15/17. And it gives me the same exact value. So hopefully that is verification that when they give you all three sides, you can use any relationship you want. And in the past, I've had when people are working together or somebody's asking questions to a neighbor, and the neighbor says, "Well, use sine." But that person asking the question might have been a person that prefers to use cosine, and they don't know why the neighbor used sine. It's preference. It doesn't matter if you're given all three. Okay. What about this one here? What about number 9? Does it matter which one we use? No. Okay. So is this kind of looks special, doesn't it? Like there's some of those terms that were in a special right triangle, right? But are they the right ones? No. Okay. What if this was a 3 here? What if this was n radical 3? Would they be the right ones? Why not? Because the hypotenuse in the 30, 60, 90 has got to be the 2n one, right? So it'd be the right components, they'd just be in the wrong positions, okay? What we're trying to get at here is that we don't know what y is based off the side length directly. We have to run through these relationships. So I want to find y. Okay, what side would n be? Opposite. N radical 5 is hypotenuse, and 2n is. Okay. So what do you want to use? What trig ratio are you interested in? Say it again. Say it again. Sine. So sine of y would be what? N over 2. N over n radical 5, right? Okay. Now, some people will argue, well, my calculator won't put n in. Okay. But what can I do here before I go to my calculator? The n's can cancel, right? That can cancel and that can cancel. I'm really left with sine of y equals, so if they cancel, I'm left with 1 over root 5, right? And now if I inverse this side and inverse this side, we should get y equals sine inverse of 1 over root 5. Okay? So we type that in, see what we get. Arc sine of 1 over root 5, 26.56 degrees. Okay? Now here's my question. Does it really matter whether I canceled those n's? Obviously, with my calculator, I can't. If I put n here and I put n down there, like, it doesn't know what to do. It won't cancel it automatically for me. Okay? But wasn't trigonometry and everything we've been talking about, isn't it predicated off of similarity? You guys remember that? So when I put n's on these, it's basically saying that you can have, if n is 1, you have a triangle maybe this size. If n was 2, it doubles, right? If n is 3, it triples. But if those triangles are all similar, then don't they have the same angle y in them? Because all similar triangles and all similar shapes just in general, polygons in general, have to have angle congruence. Okay? So what I'm trying to get at here is you can let n be anything. Okay? So I created that slider. Now n is any number I want it to be. Now, obviously, when it goes to 0, that's a problem because I divide by 0. So maybe I make that distinction. But now, even I can make it even a negative number, which doesn't really make a whole lot of sense if n is producing a distance, but it works. Okay, so if I choose any number here, it's going to say I get back the same angle, right? So if I put, 1, 5, 8, 7, 4, 5, and then 1, 5, 8, 7, 4, 5. It's the same amount as if that was, put another 1 on there, put another 1 on there. Okay, it's still the same angle, right? So it does not matter what n is. And that's why algebraically I think maybe it's useful to cancel them first. But if you're going to use a Desmos, or you've used UTI 8.3 or 8.4, just make n something. Make n 2. And plug it in and see what you get. Does that make sense? Okay. Do that one. Finding W and Z. Before we do anything, what do you think we should try to find first? Or what triangle do you think we should start in first? Start in a 30-degree triangle, because that one you know a distance about, right? This triangle over here we know nothing about. All right, so we started in the triangle on the left, right? What is unique about the triangle on the left? It's a 30, 60, 90. So we can use trigonometry. We can use Sohcahtoa if we want to. Okay? My suggestion, though, when they have a 30, 60, 90, just because in the event that they ask us to decide across from 60, Sohcahtoa is going to produce a distance that is rounded. Okay? In this case, either route would be fine because they're asking the distance across from 30, which is going to be half of 150, right? So if we use 30, 60, 90 triangles, we know 150 is equal to n. N would be 75. Is that okay with everybody? Okay. And if n is 75, that's the side across from 30. So that makes our W 75. Okay, if we were looking for W using Sohcahtoa, this would be the opposite side, and this would be the hypotenuse, right? So I'd say sine of 30 is equal to opposite over hypotenuse. So now if I go 150 sine of 30, oh, I'm sorry. Is that what I'm sorry. Well, I lost my controls. There they are. I'm sorry. So we'll start over. If my hypotenuse is 2n, because it's 30, 60, 90, that gives me n to be 75, right? If we use Sohcahtoa instead, this side would be opposite, this side would be hypotenuse. So we go sine of 30 is equal to opposite over hypotenuse. Multiply by that LCD, which is 150 in this case, and we get that. So if I type that in my calculator, we get 150 sine of 30, still gives me 75, correct? Okay. Now, where I would be cautious of using Sohcahtoa in a 30, 60, 90 triangle. Now, I know they don't ask this, but let's say if they asked for that distance right there. Okay. Through 30, 60, 90 triangles, we know n is 75. That side right there has got to be n radical 3. It's 75 radical 3. That is an exact value, correct? Okay. So no matter what they ask, you can round it to one decimal place, 2, 3, 4, 5, 15 decimal places. Once you grab your calculator and type that out, you know the precision and how accurate that value is, because that right there is exact. Okay? But if I use Sohcahtoa here, let's say, so that would be the adjacent side, and this would be the hypotenuse. So let's say I go cosine of 30 is equal to adjacent, so x over hypotenuse 150. So if I go 150 cosine of 30, cosine 30, it gives me that number right there. And I only know that number to be accurate really to that decimal place right there. Okay? But if I type in 75 square root of 3, that is 100% accurate. Does that make sense to everybody? Okay. I typed 15 for it. That should be 75. Oh, wait. 150. I put 15 instead of 150. I'm sorry. 150. That's why it's multiple 10, right? That's why we're seeing that decimal place change. So I apologize for that. But this one is a better answer because in reporting, I'm going to report 75 radical 3. Up here, I usually wouldn't report that. I could, and it'd be exact. But usually when reporting my answer, I would have to write it as 129.9 or 0.90, 0.904, something like that. Okay? So just be aware of that. And it's especially important when this number is going to be used later on to find something else somewhere else. Okay? For instance, we're going to use this number here to help find z, right? Okay? Well, if this number would have been 60, then it would have been 75 radical 3 that we used to find z. Does that make sense? Well, if I use 75 radical 3 to find z, then there's no rounding error. But if I use 129.9 to find z, then there's rounding error, and then I don't really have z. Okay? So we've got to be cautious of that and thoughtful of that as we move on. As a teacher, that's the one thing that I struggle the most with in trying to get students on board with and understanding that rounding error is an issue. Okay, and if we can avoid it, we want to avoid it. So now I want to find z. Okay, so now I'm in this triangle here on the right, correct? What side is z to the 40 degrees? Adjacent. And now I know 75. 75 is what side? Opposite. Okay, it's still opposite 40. So what trig ratio uses opposite and adjacent? Tangent. So I'll say tangent of 40 is equal to opposite 75 over adjacent z. What are you going to multiply both sides by? Multiply by z. Cancel, cancel. So it gives me z tangent of 40 equals 75. What are you going to divide both sides by now? Tangent of 40. So I get z equals 75 divided by tangent of 40. And that will generate 75 divided by tangent 40. I'm getting 89.38. Is that okay? You feel somewhat comfortable with these? What's this one? On a test? Yeah. Let's come down here. Let's go to. So this is what I really like about geometry. Because we can come down here to question 22. And we might know a lot about trigonometry. Sine, cosine, tangent, 30, 60, 90, 45, 45, 90 triangles. And not be able to answer 22, question 22, because we have forgotten maybe what we learned in chapter 6. Okay? So I like this because geometry is one of those courses, and math in general is this way, that when you come across something, you can't forget it. Okay? And I know that's a bad or not very friendly or likable statement, because we will forget things. But if we do forget things, at least we can't forget that we've come across it, and that we can go back to our resources and maybe quickly brush up on it and refine on it. Okay, refine our skills with it. So 22 talks about a rhombus. Okay, what's a rhombus by definition? That's a parallelogram. So a rhombus is a parallelogram. What'd you say, Manny? All sides are equal. Okay? So when we draw a rhombus, it should look something like that thing. Okay? All the sides are equal. Now, it doesn't tell me what my sides are, but it tells me my diagonals have a length of 4 and a length of 10. So I'm going to draw that diagonal, and that's probably the one that has a length of 4. And we'll draw a red one in here. That's the length of 10. Does anybody remember from chapter 6 what those diagonals do to each other? They bisect each other. So this little distance here is probably, if that whole thing was 10, that's going to be 5, right? And if the other diagonal was 4 in total, then that distance is going to be 2. There's one other property that is useful about rhombi. Okay, so when these diagonals bisect each other and they're perpendicular. Okay? So I just created a right triangle here, correct? Okay? I'm going back to the question. 22 says, find the angles of the rhombus to the nearest degree. Okay? Find the angles of the rhombus to the nearest degree. Well, in order to find the angles of the rhombus, the first thing you're going to have to do is maybe find that green angle. Okay, so let's call that angle let's just call it X. I was thinking about, you guys know your Greek letters at all? Like alpha, beta, things like that? You never heard those before? Have you heard of those? Okay. So in Trig, we'll use alpha and beta. Sometimes we use gamma. We use those to represent, or I guess that's omega. We use those to represent angles. So I might introduce that from time to time. We just call this x, doesn't matter. What if I'm going to try to find x, what side do I have of this right triangle? I have the opposite side, and this would be the adjacent side, right? So can I use, which trig ratio would I use to find x in? Tangent, so I'll say tangent of x is equal to opposite over adjacent. What am I going to do to both sides? Take the inverse there. Take the inverse there, right? And that's going to cancel, leaving me x equals the tangent inverse of 2/5. So we're going to figure out that. (21.8 degrees, right? Is that right? Did that answer the question, though? What's the question ask? Yeah, but it also says find the angles of the rhombus, correct? What did we just find the angle of? Yeah, we just found the angle of that triangle, right? So now, what are equal? Just be careful with how you verbalize that. I think I know what you mean. Yeah, so that diagonal right there bisects that angle right there, correct? So top angle and the bottom angle are the same. So we can double this number. So I'll just put a 2 out here in front. That doubles it. Okay. So one angle is that, right? Okay. Does anybody remember? So this is a rhombus. You told me a minute ago it was you said it's a quadrilateral with both pairs of opposite sides parallel. So, but that is the definition for a parallelogram. So this is a rhombus and it is a parallelogram. So in a parallelogram, what do you know? I'm just going to do this. What do you know about that angle there in comparison to that angle there? They're supplementary. So if I know the one angle is 43.6, I'm just call that A. If I take 180 minus that, is that giving me my other angle? Does it kind of make sense to everybody? So then, so this angle here, which is the 43 angle, is going to be the same as this one here, right? And whatever we said this one was, is going to be the same as that one. Does that make sense to everybody? So we're using a lot of what we learned in Chapter 6 now, coupled with what we have learned here in Chapter 8. Can I also, if you remember, this was 2, and this was 5. Can I find this distance here? What would that distance be? How would I find that? If I know this is 28 degrees, or approximately, could I use Sohcahtoa to find it? Yeah. Okay, but there's a better way. Here's Stagnant Theorem. 2 squared plus 5 squared, that's 29, right? Take the square root of that. That's radical 29. Now, I should be able, like I said, if that's 28, I should be able to say opposite in hypotenuse. So let's say sine of 28 is equal to 2 over, we'll just call that distance S for side. So side would equal 2 divided by sine of 28. So let's see if we can do that. And then I want to talk about the error that can happen here. So this distance right here, I guess it wasn't 28, it's 21.8. Okay, so 21.8 instead of the 28. So everywhere I wrote 28 down here, rewrite it as 21.8. If I go 2 divided by the sine of 21.8, Okay, 0, 1, 4. See how as I change the decimal precision, the actual quantity is changing, right? Because that's the rounding error. Okay. Now, if I put A down here, and it plugs in this exact value, okay, which would really be typing in 2 divided by sine of arc tangent of 2/5, which we can do, okay, that's just a lot messier looking, right? Okay, but because of Pythagoras, we could actually say that's the same thing as square root of 29. That makes sense there? You see these two values are the same, right? Okay, now, the Pythagorean theorem, without the use of a calculator, that is a better procedure and result than using Sohcahtoa, because if I use Sohcahtoa, then chances are to generate an actual value that I can put on the number line, I'm going to have to round that 21.8 number. Okay, maybe I round to, if I go 2 decimal places like that, let's call this B. Let's call this C. If I go B minus C, now we have, what, there's the tenths, hundredths, thousandths. We have 3 10,000ths error. Does that make sense? I can fix that error by going out more decimal places. Okay, now that went from 3 zeros and a 3, now it's 4 zeros and a 9. I can go even better. Okay, now we got 5 zeros and a 2. That kind of makes sense? And that's the idea of rounding error. Okay? If I can minimize it or completely mitigate it, completely get rid of rounding error, that is the approach that I want to take. Okay? I'm going to stop there for today.